so this chapter is very, very simple. And I guess my goal is to cover the chapter completely today. And then on Wednesday, we can meet only 4 questions because we are supposed to finish today. So, so if you have your files, please open your PowerPoints and open your Excel file. So, so we are going to start. So chapter 5, continuous random variables. So we are going to look at what are the continuous probability functions. And we're going to look at 2 of them, the uniform distribution and the exponential distribution. So, so these families of continuous distributions are basically well, so one of them, the most important, is the normal distribution. So if you notice, we dedicated one entire chapter for the normal distribution. So so some of the properties of these continuous probability distributions. So this is the graph on a continuous probability distribution is a curve. So we are gonna, well, in this case, we're gonna see the uniform that is a rectangle. But the idea is the area inside that figure, which we're gonna call curve, is gonna be representing the area under the curve, right? So and remember the area under the curve for probabilities is equal, the whole area is equal to 1, right? So this the curve is called the probability density function. Is abbreviated PDF. So, and we are going to use the symbol f of x to represent the curve. So f of x is the function that corresponds to the graph. We use the density function f of x to draw the graph of the probability distribution. So the goal is that we are going to look at the cumulative distribution function. So we are going to look at the area under the curve, which is given by the different functions called the cumulative distribution function. So so the cumulative distribution function is used to evaluate probability areas. So the outcome is not measured, is measured, not counted, as in the previous chapter. So the entire area under the curve and above of x-axis is equal to 1. So and why 1? Once again, that is so if we have different so 1 is the area under the curve, and should be the addition of all the probabilities in our case. So probability is found for intervals of x values rather than for individual x values. So in the previous case, we were able to find specific values. Here, specific values do not make too much sense. What makes sense is the interval between them. So this is an example of the cumulative distribution. So this is called the uniform distribution. So let's assume that our distribution falls between 2 and 9, 2 and 8.5, right? So those are going to be the extremes. So we are going to say that, so this is C and this is D. So the probability that X lies between C and D is the probability that the random variable X is in the interval between the values of C and D. So we're going to be able to pick 2 different points, and we can also find the area under the curve. So so any area can be, we're going to be able to figure out what is the probability of an event that occurs between 2 and 6. So in this case, so the probability that X is between C and D is the area under the curve above the axis, above the x-axis, to the right of C and to the left of D. So so any probability that is going to be here, which is 100%, is going to be located to the right of this and to the left of this point, right? So assuming that this is C and this is D, right? So the probability of a single point, let's say I want to know the probability of X of 7, probably doesn't make any sense because I am measuring the area. I can measure the area from 7 down or 7 up, but 7 itself is not going to be possible. So the probability of C is going to be equal to 0. So that probability that X takes a single individual value is 0. Okay. So that is part of this explanation. So the cumulative also, the area below the curve, above the axis X, and between X equal to C and X equal to C has no width, and therefore the area is 0. So it's a repetition of this case. So when we have a single point, we don't have any area under the curve. So so the probability that X lies between C and D is the same as the probability that that X is less or equal to C, and so it's between these 2 points, including these 2 points, right? So so these 2 points included. So because the probability is equal to the area. So when we are saying that the probability is less than, is also is the same as saying that is less than or equal, right? C is less than or equal to X. So so in this case, we can write the notation in this way, or we can write the notation on this way. So in the two cases, we're assuming that we are looking at the cumulative area, right? So, and what does that mean? So we are going to be more specific. So here we have the first of the continuous distributions. We have several of them. So the examples that we are going to analyze today is going to be basically 2 of them. So this is the uniform distribution. This is called the exponential distribution, and this is called the normal distribution. As you can see, the area under the whole curve, so in this case, even though this is not a curve, but we call the curve, so is equal to 1. So we are going to be able to capture the probability of events within certain interval, right? So so in this case, we have the uniform distribution, we have the exponential distribution, and we have the normal distribution that we are going to analyze next time. So we begin by defining the continuous probability density function. So we use the function notation x of x, and we define this function so that the area between it and the axis is equal to the probability. So since the maximum probability is 1, the maximum area is also 1. So in this case, is there any probability that 1 is going to happen? Well, the answer is no, because it's not within this area. So probably something similar happens here. So so we cannot measure probabilities that are outside of our area. So for continuous probability distribution, the probability is represented by the area under the curve. So we have repeated that several times. So we have the examples for the continuous distributions. So we are going to look at one case in particular. So as I mentioned, the first one is a uniform distribution. Just imagine, well, I was reading an example of this. And for example, you are in a golf court and you have people playing golf, right? In a golf court. So you have people playing golf. So you know that for a fact that people, when they hit the ball, they can reach no more than, let's say, 800 meters, right? I don't know if that is true, but so that is the boundary on the other side, right? So we are going to be wondering that people are going to be probably hitting the ball between 0 and 800 meters, right? So we are going to form a uniform distribution in that sense. So if somebody comes in and said, what is the probability that this person is going to hit, less than 600 meters. So we can compute that thing. So that can be an example of what we want to do. So uniform distribution is a continuous probability distribution and is concerned with events that are equally likely to occur. So if you are playing golf, you can either hit the 800, the 600, any of these points can be achieved by the player, right? So when working out problems that have a uniform distribution, be careful to note if the data is inclusive or exclusive. So, so the notation for the uniform distribution, so this random variable follows a uniform distribution when we have two different parameters, A and B. So in this case, when we have these two parameters, so we have a beginning and an end, right? So, and we might have two different points here that we are going to call x1 and let's say x2, right? So, of course, if I want to take this x1 from the beginning, so that can be also x1, right? So, so these two different points are not, so can be arbitrarily chosen, right? So I'm gonna replace the thing, right? So the area that we might be willing to analyze is gonna be the one that lies between these 2 points, right? So that's basically very simplistic, because in this case, what do you need to measure the area under the curve? Of course, we need the height and we need the base, right? If you have the height and the base, so you have the area under the whole thing. If you have the base and the heights, you can measure the area under this curve, right? So it's gonna be very simple. So we are gonna define some things very clearly. So so the notation is that this random variable follows a uniform distribution with two parameters, A and B, where A is the lowest value of X and B is the highest value of X. So that's what we did here. So the probability density function is gonna be equal to f of X 1 divided by B minus A. So we're gonna subtract the smallest from the highest, and then that is gonna be divided by 1, right? So in this case, we are assuming that B is always higher and this is lower. I don't think there is any possibility of being 0. Well, probably it can be 0 when these two numbers are exactly the same. That's what we argue at the beginning. So in order to find the heights, so this difference between A and B is gonna give me the base, and this f of X is gonna give me the heights. So, and also we can find the mean value by adding A and B and dividing by 2. So let me make a comment here. I think I made a mistake. If you go to the uniform distribution, that should be a plus, not a minus. I think I made a mistake in the formula. I corrected it later. So please go to your formula and make sure that the mean is gonna be equal to B plus one, B2 plus B2 plus B1 divided by 2. Okay. So that's what we are doing here. This is the mean value, and this is gonna be the standard deviation. So so the standard deviation is gonna be the difference. It's gonna be the base square divided by 12. 12 is a constant here, and then we're gonna take the square root. Okay. So so this is gonna be simple. So all we need for this distribution is gonna be the beginning and the ending, and then we're gonna need two different points in order to find the area on that particular case, right? So so let me continue. So we have the this uniform distribution, we have two different, we have the lowest and the highest value that determine the base. In order to find the heights, I'm gonna divide 1 by b minus a, right? We have the formula for the mean, and we have the formula for the standard deviation. So in this case, this is very simplistic too. So let me make this smaller, and let me take my face out of this picture so we might have more space, right? Here, so the amount of time in minutes that a person must wait for a bus is uniformly distributed. So in many cases, we need to know what kind of the distribution is the one that we are thinking of. Not many cases, I think the most important and probably most widely used distribution is the normal distribution. Sometimes we are so used to the normal distribution that we don't recognize this uniform distribution very well. So we have to think about how to figure this case, right? So in many cases, and especially for teaching purposes, most of the time you know the distribution. So in many cases, what happens when you don't know the distribution? Well, basically you start researching in the literature. You go to online resources and find the case that you want to analyze and see other papers that people are using. And then you see, oh, these guys are using a uniform distribution. Probably that's the one I should use. In many cases, I mean, I don't know how obvious it is to use this uniform distribution, but in this case, you're always gonna know that this is the type of distribution that you need to use. So, so the amount of time is uniformly distributed between 0 and 15. So in this case, there is a maximum point, and this point has been, so in this case, we have two different points, 0 and 15 minutes, right? So in this case, this is gonna be 0, and this is gonna be 15 minutes, right? So here, I made just a very simple formula. I said subtract B2 minus B1, and that is gonna be the difference that we need to know to compute the base of my rectangle. So in this case, this is gonna be 0, and this is gonna be 15, right? So those are the values here. So suddenly, well, I almost fix everything because I already computed the 1 over the base. So 1 over the base here, 1 over the base is going to be 3, so it's 6%. Let me make this a little bit less, like at least 3 decimals. Oof. So 0.67, right? So so in this case, so we figure out this case. So we have the probability, the heights of these uniform distribution, and we have the base. So if I multiply the height, the height times the base, what do you think is going to happen? Well, something very simple. That is going to be equal to 1. So if you multiply the height by the base, we are going to get the rectangle, the area of the rectangle. And we know that this is a probability distribution. Therefore, the value should be 1, right? So that's how we can make sure that what we are doing is right. So now I'm sure that the whole area is 1. So so here, the question is, what is the probability that a person waits fewer than 12 minutes and 5? So in this case, I'm gonna find, so in this case, my X, so that's the reason so my X in this particular case is gonna be 0, right? So my X1 is gonna be 0. So in this case, I'm gonna compute the area under this curve, right? So so here I'm gonna use x1 as 0. So this is my x1 is gonna be 0. And let's say the x2 is gonna be 12.5, right? So let me write it here. It's gonna be 12.5. So that's the question that I want to answer. What is the probability that the person waits less than 12.5 minutes? So in this case, it's going to be 12.5. Remember, if I press enter, all these things are going to be solved, right? So in this case, the probability is going to be 83%. What I did is I followed the formula. You multiply the base times the heights. So the base in this case from here to here is 12.5, and the heights remains the same, 0.067. So the probability of this is going to be 83%. So what might be here? I'm going to say what is the probability that x is going to be greater than 12.5? Well, that's also a very good question. I think we can solve this very easy by using the idea of the complement. So rather than using this, I'm going to compute this area. So I am going to say 1 minus the area under the curve, right? And why did I do that? Well, because I know that the complement, if I add this probability plus its complement, I am gonna get 1, right? So that's gonna be my the complement of this. So and I think that's basically it. So there is another question that we can be able to answer, like for example, what is so in this case also I forgot. So we have the mean value. So the mean value, as we can see here, is going to be B2 plus B1 or B1 plus B2 divided by 2. Of course, it's the mean point. So that can be also the median value. So so we can find it very easily. So the standard deviation is going to be given by the square root of the base squared divided by 12. So that was the one that we discussed here. So the base squared divided by 12, and then we take the square root of this. So I build this formula very easy. So if you are using this, the only inputs that you need is these ones. So when you find the base and the f of x, so we have the heights and the base. So and then we have the two parameters here. Okay. So so in this case we are good. So but let's think that so you might ask yourself, so why is, so let me erase this. Let me erase this. Erase this. Erase this. Erase this. So so what is the 50th percentile? So for example, here I think so we can find the 50th percentile by multiplying. So what is the number here? So if this is from 0 to 15, what might be the, let's say the 75th percentile, right? So almost 3/4 of the distribution are gonna be here, right? So that might be the 0.75 percentile. So 75% is going to be here, right? So I want to know the number here. So this is 75, right? So I want to know what number corresponds to the 75th percentile. So what I'm going to do here is basically type, well, I already built the formula here. I am multiplying the percentile times the base. So I'm going to find the number that fits here. So if I want to know the 75th percentile, so this number is going to be 11.25. So this value here that represents the 75th percentile is going to be 11.25, right? Okay. So you can solve this. So this is very easy. Basically, let the time needed. So the amount of time a service technician needs to change the oil in a car is uniformly distributed between 11 and 21 minutes. Let's do this here. So let's erase this. Let's erase this, and you can use so the same graph. So let me erase the points that we don't need. This is very nice. I barely use it, but it's very nice. So I don't have to do so much, which I like. I'm lazy. So in this case, we have, so we also get rid of this. We get rid of this. So in this case, we have, it says less the amount of time a service technician needs to change the oil, and we say that is uniformly distributed between 11 and 21 minutes. So here we have A, that is 11, and this is 21 minutes, right? So we have the base. So in this case, we can do the following. So we have 11, which is going to be here. Let's choose an arbitrary point. And this is 11. And this is going to be 21, right? So my uniform distribution is going to be as follows. So that is going to determine my area under the curve, right? So so I have the so I know that this is going to be 0.1, and this is going to be 10, right? So if I multiply 0.1 by 10, it's going to be 1, right? So let X, so that's so we are writing a random variable in words. So here is the time needed to change oil on a car. So write the distribution. We are going to use the same notation as here. So X so here X follows a uniform distribution with parameters 11 and 21, right? Doesn't look like this, but this is an 11 and this is a 21. So graph the distribution. That's what we did here. So find the probability that this is more than 19. Okay. So I'm gonna do the following. This is gonna be 19. So I can compute the area to the left. That's what I'm gonna do. So so my X here is gonna be 11, and this is gonna be 19, right? So so this is the and this is greater than 19. So let me fix it. So greater than 19. Okay. So so here this is gonna be 80%. And if I here, that's the beauty. I didn't do anything, and I already know, because this is a formula, so I know what is the complement. So the area under this is going to be 20%, right? So now I want to compute the 50th percentile. So I want to know what is the 50th percentile. So once again, that's going to be here. So what is the 50th percentile, right? So it's gonna compute the area to the left. So here, what I'm gonna do is I'm gonna type 0.5, which is the 50%, and then the number is gonna be 5. It was fine last time. Find the 50th percentile. We are doing the percent times the base. So the base is gonna be 10. 50 percentile, 0.5. So let me check this result because that doesn't make any sense. 5 is outside of this. So I'm gonna check this because so this is not the 50th percentile, right? So I'm gonna check on this. So probably what I did here, the percent, or probably here, yeah. So I was taking this as, so it should be 16 here. So so that's probably the number I should use. So because I was accounting in the previous, I think this is a flaw from my little computation. So it's giving you how many points you have to add. So in this case, this number is going to be 16. Okay. So I hope it doesn't cause any problem. So so that's going to be the middle point between 11 and 21. So so that's going to be the 50th percentile. So half of the distribution goes to the left, half of the distribution goes to the right. Okay. So so it has to be the number that defines the middle point. So remember, we also define this as the mean value, right? So that's the indication that we need to follow. So that was a little flaw from my my computation. It gives you the numbers that you have to add after the lower point. So I hope that this is not a big turnoff. So the second time, so here that was very simple. This little thing allows you, and I see that at least there are 1 or 2 examples that where you can use this little thing. So secondly, we have the exponential distribution. So this exponential distribution is basically often concerned with the amount of time until some specific event occurs. For example, and this is a very good example, the amount of time beginning now until an earthquake occurs has an exponential distribution. So so that's a very good question. You live in, like, for example, Mexico City is an area where earthquakes are very often. So you might ask scientists, okay, this was really bad. In 1986, we had a big earthquake that destroyed almost half of the city. And surprisingly, the same day, like 20 years later, there was a similar earthquake. So can we predict this with an exponential distribution? Well, probably that might be good for an educated guess. So we can probably predict that event. So, and of course, it's not a predict. This we can compute some probabilities that are based on the data that we have. So other examples include the length in minutes of long distance business telephone calls, the amount of time in months a car battery lasts. So you want to know how much your battery is gonna last. You know that something is coming at some point, and you might be wondering what is the likelihood that this is gonna occur in the next couple of months, or the amount of time. So it can be shown too that the value of change that you have in your pocket or purse approximately follows an exponential distribution. So so this is going to be also very simple. We are going to look. We want some values only. So values for exponential random variable occur in the following way. there are fewer large values and small values at the end. So so that's the reason we have this. So this value in this case doesn't capture the heights of the distribution. So in this case, for the exponential, what is computing is what is called the decay factor, right? So you are looking at what is going to happen, and the probabilities are fading as we move on time. So for example, the amount of money customers spend in one trip to the supermarket follows an exponential distribution. There are more people who spend small amounts of money and fewer people who spend large amounts of money. So the exponential distribution is widely used in the field of reliability. So reliability deals with the amount of products, how long a product is going to last. I think that makes sense if you are a computer maker, if you are producing cars or producing anything. You want to know what is the probability that your product is going to last for the next couple of months, years, or something like this, right? So this basically, I want to say that the idea of this was taken from this video. I also send you two more. So this is going to be very interesting. In order to solve the exponential distribution, we need the value of mu, and we need the value of the random variable. So if we have these two elements, we are going to be able to find the probability that this event is going to occur. So we are going to compute, once again, the area to the left. So, and that might be also the case as in the uniform distribution, that we have to compute the values between two different random variables, right? So in this case, we also have the same. So we can have a case where we have to compute the area between two different places. So this one, so if we are using one random variable, we are assuming that we are computing the area to the left. So in this case, so we are going to compute the area between two different cases, right? So so in this case, let's see what it says. So let X be the amount of time in minutes a postal clerk spent with his or her customers. The time is known to have an exponential distribution with the average amount of time equal to 4 minutes. So the average amount of time means that this is the mean for the time this person spends with his her customers, right? So so what happened is we are going to use the mu, and we are going to find the reciprocal. So the reciprocal of a number, for example, the reciprocal of 4 is going to be 1/4. The reciprocal of 5 is going to be 1/5. The reciprocal of 1/1, so the reciprocal of 1,000 is 1/1,000, right? So we are going to find in this case that the mean is going to be 4. So in this case, I ask Excel to divide 1 by the mean. So if I put 4 here, I'm going to find the value of my reciprocal. That reciprocal is going to be called lambda, right? So in this case, also we know that sigma is equal to mu. So the standard deviation of the exponential distribution is going to be equal to the value of mu. So in this case, I just need to type the 4. So I need to type, what happened here? So I needed to type the 4 in order to compute the value of the mean, right? So this is the mean, and this is going to be the standard deviation. So what happens, like, for example, so x is a continuous random variable since the time is measured. It is given that 4 minutes is mu, so we transform this, and that becomes the reciprocal of 4, which is 0.25. So 0.25 is going to be the decay factor right here, right? So this value is going to be equal to 0.25. So we know the standard deviation is going to be equal to mu. So, and we use the notation x follows an exponential distribution with a parameter that is captured by this decay factor, right? So in this case, it's called mu, it's called m, but in many cases, it's called lambda. So lambda is going to represent the decay factor. So to make the long story short, so we are going to measure the area under this curve. For example, it says using the information from the previous exercise, find the probability that the clerk spends 4 to 5 minutes. So so let's do something first. So let's say what might be the probability that the clerk is going to spend less than 5 minutes, right? So the mu is 4, but I want to find the area that tells me the probability that this person is going to spend less than 5 minutes. So I'm going to type 5 here, and I'm going to get that probability. So that probability was use this exponential distribution. So I use equal exponent that dist, and then I type the random variable. In this case, it's going to be 5, followed by my lambda, which is going to be the decay factor, and then followed by the word true. True, remember, gives you the cumulative area under this curve. So so we have a 71.3%. So what might be the probability of, so I'm going to type it here, the probability that x is greater than x1, right? So assuming that, so this is x1, right? So, oh, I know. This is not Greek, should be. So the probability that x is greater than x1. So of course, if I have this area, all I have to do is 1 minus this area, right? So we have the same results. So so because I know this area, all I have to do is to subtract the area from 1, and I will find the area under the curve. So let me make it nicer. There are so many decimals. I always like to push this, but remember, if I click on this, so I see the formulas. So that means that all the decimal points are going to be secure. So here, so the question, the original question of the case is, what is the area under the curve when k is 4, k1 and k1 is 4, and k2 is 5. So find the probability that x is going to be between 4 and 5 minutes, right? So I want to find what is the probability that the person is going to spend between 4 and 5 minutes with a customer. So so basically, it's very easy. I already wrote the exponential, the Excel function for x1, the Excel function for x2, and this is the difference. So in this case, we're going to subtract the lowest from the highest, and that's going to be the area under the curve, right? So we can do it by hand, or we just can ask Excel to build it. So all I need here is the 4 and then the 5 minutes, right? So we have, I did something wrong. That is not surprising on me on the typing 4. Okay, so here is gonna be 4, and here, 4. Something happened with my mouse, doesn't work, and this is 5. So we have the area before here. So let me make a note. So this 4 measures the area from 4 to the beginning of the distribution, and the other one measures the area from the 5 to the beginning of the distribution. All I have to do is to subtract the smallest from the highest, and then I'm gonna find the area under the curve. So also, I want to know, for example, I know that this is an 8%. So I know that this point here, the 5, represents the, here is the 71st percentile, right? So this is something that I know. But I want to know what is the 90th percentile. So I want to know what is the 90th percentile. So all I did here is I follow this formula. So in order to find the value of K, so what is the number that represents, well, in this case, they were asking for, or the 50th percentile, so 0.5. So the 50th percentile, so I use this formula. I took the natural logarithm. So let me see if I can. So here's the natural logarithm of the percentile, and then divided by the negative value of my decay factor. So so we have the decay factor equal to 25. So so this is going to be the negative value, and this is going to be the logarithm of the percentile. So in this case, I can find that the value for my so for the 50th percentile is going to be 2.77. Okay. So here the value is going to be 2.77. 277. Right. So and that probably is it for today. I think we have one more slide. So so there is a case that you can do using this. So please solve this at the end and give me the results. Okay. So that might be the homework. So the second part of Excel is going to be very easy. And then is there any question? Is there any question?
No, we're good.
Okay.
I think we're fine. I think we got what we got with what you were talking about today.
Okay, that makes me very happy, and I will be around next Wednesday, so I'm gonna be online next Wednesday. If you have any issue, any problem, I will be available. So technically speaking.
Oh wait, I'm sorry, Professor. I just want to make sure this chapter 5. Do you want us to combine it with chapter 4 and submit it together, or are you gonna do it separately?
Well, I mean, I think you can. So do the same in the previous Excel file.
Okay.
Copy these 2 tabs, and just do it. And probably so an additional exercise is to solve 511. That's it.
Okay.
It's gonna be very simple.
Thank you.
Okay, sure. So I'm gonna be online next this coming Wednesday. So if you have questions, and